So today we are going to look at the mass transfer fabrication. Okay, what we have seen in the last class. What we have seen in the last class. Quantitative analysis of mass transistor that we have seen, right? Okay, so now what is the outcome that we have drawn from that? Okay, so we have derived the IDS value, right? So we have derived the IDS value. So what is the IDS value at cutoff region? What is the IDS value at cutoff region? It is 0, right? What is the IDS value at linear region of operation? It is, sorry, IDS value is equal to UN into C oxide 2 W by into VGS minus BTH CDS. So this is the linear mode of operation current equation, right? So as we keep on increasing the VDS value, IDS values also increases linearly. That's what we can observe about mass transistor operation in linear region. Okay. Now, if the mass transistor is operated in saturation region, then what is the current equation? So this is how 1 by 2 into mu n into C ox into W by L into VGS minus VTH whole square. Can you guess at what condition this is holds good, this equation? At what value of VDS this equation holds good? So under the condition of VDS is greater than or equal to VGS minus of VTH. So the detailed discussion we have studied in the previous sessions, right? So this is what important. Okay, just we have started from mass capacitor, from the mass capacitor to mass transistor, and its characteristics that we have seen. Now, how do we fabricate this transistor in a semiconductor? Okay, so that means we are the symbolic representation we are converted into a real circuit or real device. Okay, that's what the next step that we are going to do here. So that is called mass transistor fabrication. So it is all about how do we manufacture the transistor. How do we manufacture the transistor? That means a physical process flow that we want to tell about it, right? Okay. So by the way, we know that this is what the symbolic representation of a mass transistor, right? This is a symbolic representation. Of course, it is a 4-terminal device. We have a gate, drain, source, and body. Agreed? Now, we need to realize this one on a semiconductor. Okay. So we have to take a semiconductor, piece of semiconductor. We have to do this one, right? So in order to do this one, what are the different processing steps are there that we should know? Okay, it is not just that we cannot make a transistor. We have to follow some kind of steps, right? So these are the essential steps that we have to follow in order to make a single transistor. Of course, it's not necessary to a single transistor. Millions of the transistors also the same process. Okay, if you learn about how can we fabricate a transistor, single transistor, that is applicable for n number of transistors that is available in the IC. Only the difference is the routing of the transistors, right? So therefore, these are the essential. Sorry, these are the essential steps that we have to consider. Okay, so these are the essential processing steps, and there are the different methods are there actually in order to fabricate this one. Actually, this is what the physical representation. Okay, physical representation of a transistor. Okay, we have a body, we have a source, we have a drain, we have an oxide on top of it, a gate, and it is a metal contacts. Metal contacts. So let us see step by step how can we form all this kind of materials on semiconductor. Okay, and we are going to use the polysilicon gate technology. So we are using a polysilicon gate technology. What does it mean? That means if you consider the transistor here, okay, this is the transistor, right? So whatever the gate, polysilicon material, okay. So why we have to use this one? As we can see here in this diagram, it is actually represents the metal actually. Okay, so metal that we have used as a gate generally. Initial days, people were used to metal, okay, but they found some kind of problem. So after source and drain realization, we have to place gate. That is the process that we have to do. So because of that one, the formation of the source and drain needs very high temperature. Okay, so when we are realizing, so sorry, we have to create a first gate first of all. Then we have to realize source and drain. First, we need to realize gate. Then we have to realize source and drain. So while we are realizing the source and drain, it needs a lot of heat, the temperature. Okay, very high temperature only we are able to diffuse something into the semiconductor. So while doing that one, metal will be disappear. That means metal will be melted. Why? Because the melting point of the metal is very less when compared to the temperature requirement for the source and drain, right? So that's the reason why the people think that okay, we don't want to use the metal as a we don't want to use the metal as a gate because of this problem. But you may ask the one question. So first we should first realize the source and drain, then we can put a metal. An option is there, right? There is an option is there, right? But the problem is alignment problem. There will be a alignment problem because source and drain must be something like this. For example, here is the source, this is the drain. After that one, if you place a gate something like this, the channel is discontinuous. So that actually exactly from this one to this one, it should be there. Channel should be from here to here. That means the gate is also should occupy that particular place. So there may be a lot of chances are there. The misalignment is there if you are placing the metal after the source and drain. Okay, so that is the problem actually. So therefore the alternative is that okay, first of all I want to release the gate because of to maintain the alignment, to keep and source and if you want to reduce the problem of metallization, metal melting point problem, that can be removed by using next another material that is called polysilicon gate material. Okay, so therefore polysilicon has highest melting point. Okay, so whatever the temperature that is required for source and drain cannot melting the polysilicon. Okay, so therefore we are able to maintain the proper polysilicon gate on top of the source and drain. Agreed? Okay. So therefore that's what we can say that polysilicon gate we have to use it, and this is a self-alignment technique. As I mentioned that, okay, we did not bother about whether the channel is continuous between the source and drain. We don't bother about it, right? So it will be continuous. So therefore, this is the technique that normally very popular methodology in industry people are using. But of course, there's nowadays so many methods are there, but this is the usual practice the people are using, right? So let us understand how to form a substrate first of all. First, we need to create substrate. First, we need to create a substrate. So in order to create a substrate, we have to use the process called crystal growth. What we can call it as crystal growth. Okay, let us see what is the crystal growth. So, do you know what is the natural form of the silicon? Do you know what is the natural form of silicon? Natural form of the silicon is a powdered form actually. It is in the powdered form. So that must be converted into a single crystalline silicon. Single crystalline silicon. That means that something like this. These are called ingots. So these are called ingots. Normally we can call it as ingots. Okay. So we have to take a powdered silicon. We have to take a powdered silicon. We need to melt this silicon in order to form a liquid. Okay. After that one, just we have to use some puller here and drag upwards. Okay. Therefore, what will happen? So when it is enter into the air, so that will be solidified. Okay, the liquid converted into a solid then. Okay, powdered form is converted into liquid form, and the liquid form is again converted into the single crystal silicon. So this is called single crystal silicon. This normally we can call it as ingot. Ingot. Okay, so the process of making a single crystal silicon, okay, in order to make a substrate is called crystal growth. Okay, the process of converting the powdered silicon into a single crystal silicon to make a substrate is called crystal growth. As simple as that, right? So this is the first step that we have to follow in order to make any transistor. In fact, whatever the chip that you can use, so whatever the chip that you can use in your laptops or maybe in your mobile phones, whatever it may be. So first they will create a substrate. First they will create a base material, right? So that base material, how they can make? So this is how they can do it. So this is actually they will do it in fab labs. Okay. So they put different type of laboratories are there, so they can make this kind of thing. Okay. So therefore, how do we make? What is the thickness of this one? What is the diameter of this one? So that's depending upon the requirement. Okay. So therefore, 12-inch. Actually, it is in the diameter of the chip is actually measured in terms of inches. It's a 12-inch diameter wafer. Normally, so we have to cut this wafer into different pieces again. Of course, this wafer, this ingot is cut into different pieces. One piece we can call it as wafer. One piece we can call it as wafer, right? So in the wafer, we are going to make different kinds of chips actually. Okay. So for this is one chip. So like this, these are all the chips. We can see that whatever the square boxes are there, all this will be considered as a chip. So one chip on top of the chip, we have to make all this necessary component. We can modify that chip to make transistors, resistors, capacitors, somehow something like that, right? So yeah, so this is what the information regarding the crystal growth. Okay, fine. Okay, so this is all about the wafer. I have given an example here. It is a wafer. Okay, so wafer has got different different squares. One square we can call it as a chip. Okay, so this is the one chip. The chip consisting of these many number of nodes, so millions of transistors will be there. Okay, not only the transistor, of course. If you want to make a memory, if you want to make a resistor, if you want to make a capacitor, we use the transistor only. Okay, so we are not going to use a dedicated capacitor structure or nothing like that. We are going to modify the transistor in order to act as a resistor, in order to act as a capacitor. Most of the cases. Okay. Initial days they have a dedicated way they have realized that one. Now the transistors are sufficient to make that one. For example, yeah. So if you want to make, for example, 10 kilo ohm resistor, for example, okay, that means we have to take a material, P-type material they will consider. the dope, depending upon the doping concentration, the resistivity value will be defined. So that is the one way, or by using the transistor also we can do it. So just we have to, instead of source and drain, they are going to consider it as a 1 or 2 terminals, and they want to use only uh, just we have to place on top of it some kind of diffusion material. It will be acting as a resistor. Okay, so that means the point is that transistors are modified such a way that it will be acting as a resistor capacitor in addition to the transistor's operation. That's what we can say. Okay, as you can see here, the wafers are typically 75 to 150 nanometer in diameter. Okay, so inches are nanometers, so we can consider this. Okay, 0.4 mm thickness normally we consider. Okay, and the boron impurity concentration is the concentration value something like this: 10 to the power of minus 15. Sorry, 10 to the power of plus 15 per centimeter cube. So these many dopant atoms that we have to diffuse into the semiconductor in order to make either the N-type semiconductor, P-type semiconductor. Initially, ingots are intrinsic semiconductors, right? So later that we have to convert it into extrinsic semiconductor. Why? Because to improve the conductivity of the semiconductor. Okay. Okay. So therefore, this is the general wafer specification usually. So when you go to the fabrication lab, they will tell that, for example, if you're there in the maybe IISc Bangalore, or maybe because their sense lab is there actually, or some other IITs, or maybe abroad, if you go, there's a specific fabrication labs will be there. Okay, they will give the specification. According to this one, you have to grow the wafer. So the particular thickness, particular the doping concentration, you have to maintain. Okay, so this is the one part actually, and that's a different issue. And now, so somehow we have realized that transistor. So somehow we have taken the wafer, right? So therefore, this is the wafer, right? So this is the wafer, right? This is the wafer. So I've cut into different pieces, for example. This is the piece I'm considering. So middle one. So what we can say that on top of this one, and that means if you see the front view, for example, if this is the square, if you see the front view, okay. So if you view the front view, if you are performing some kind of operations on the top, we are not able to see that one, right? For example, in the substrate, I want to make first of all gate oxide. On top of it, polysilicon I to place. On top of it, some metal plate I want to do it. If I'm looking on the top, I'm not able to understand what are the different things are there on top of it. But whereas if I see in the side view, I can see. Okay, so the side view, if you observe the side view, first one is a substrate, on top of it an oxide, on top of it the polysilicon. Therefore, side view is we can visualize very easily than the top view. Okay, so that's the reason why. So this top view, instead of discussing about the processing steps, instead of viewing at the top view, we are going to view at the side view. Okay, side view we are going to see. Okay, that's the reason why this is the side view actually. It's not the top view. Please understand that this is how we can say that. This is the top. Agree? So that therefore we can understand what we are doing on top of it, right? Now, so the first step is we have to create a substrate, that to P-type substrate. Why? Because P-type substrate, I am interested to fabricate N MOSFET. So did you remember what is the substrate for N-channel MOSFET? P-type substrate is required. That's what we studied in the previous classes, right? Next. Next one is very important one is field oxide. It's a very, very important step is field oxide. As soon as we have a P-type substrate, okay, we need to cover the entire surface with the silicon dioxide. Okay, so that is called field oxidation. What we can call it as field oxidation. So what do you mean by field oxidation? We have a silicon here, for example. Okay, we have to form silicon dioxide on top of it. SiO2 I want to realize. Okay. So how do we make this SiO2 on top of a silicon? Just what we have to do, just place this semiconductor in an oxygen chamber. You place that one in an oxygen chamber, okay, and raise the temperature, okay. So then on top of it, the oxygen is react with the silicon, then it can form silicon dioxide. When oxygen is react with silicon, it can form silicon dioxide. This is the very popular method, or we can say that because of this mechanism, IC fabrication is evolved in a drastic manner, I can say that. Okay, so because we want to cover the entire surface with the insulators. Okay, for example, this is the actual area. I want to cover this actual area into. I want to cover this actual area with the insulator. So I have to take outside insulator and I have to put it on that one. It's very costly actually. Okay, but in a simplest manner, we can form an insulator on top of the silicon by using the oxidation process. So that oxidation process is how can we do what is meant by oxidation process? Forming the silicon dioxide on top of the silicon. How can we make this one? Just place this silicon in an oxygen chamber and raise the temperature, automatically silicon dioxide will form. So especially this way of crude method of forming the silicon dioxide is called field oxidation. It is called as field oxidation. Okay. So why it is called field oxidation, we will see after some time. Okay. So therefore thickness is actually few thousands of angstroms that we have to do. So what is the thickness of this one? Thickness of the oxide is few thousands of angstroms. That is the thickness. Of course, the thickness is very lesser than that of the substrate, but on top of it, we have few thousands of silicon dioxide thickness is required. Okay, are you getting? So, for example, if it is a top view, for example, or something like this, a top view. If I form, for example, on top of it, for example, I'm using the silicon dioxide. Are we getting what is the under the green color? We cannot predict that one. But if you say that in the side view, it is possible to say that one. Okay, because of thickness we are talking about. By observing the thickness, we can say it, right? So therefore, this is what our silicon dioxide. So for what we have seen, first crystal growth, that the substrate is formed. The second one is field oxidation that we have done. So why we have done field oxidation? That's the question. Okay, so that means I'm going to perform some kind of operations on selected portions, not in all the portions, selected portion. So you can see that we can, if you observe, the gate is at the middle, right? Gate is at the middle. Source and drain are at the adjacent to that one, something like this. Substrate is somewhere else here, something like this. Okay, that means at different places of substrate, we are performing some kind of operations, right? So that's the reason why at a time we cannot remove all the things we can do, perform all these things. So step by step that we have to do that. So therefore, whenever you perform some kind of operation, some kind of thing in a particular region, for example, if you're doing some kind of thing here, so this area should not be disturbed. This area should not be disturbed, right? So that must be remain same. So that's the reason why the silicon dioxide will act as an insulator to protect the area under this one. Okay, whatever the area under this one, the oxide below the oxide, whatever the area is, that is not at all exposed by any kind of radiations. Okay, that's what we will see now. How exactly what is the meaning of this one? Okay, so now my intention is that I want to create gate oxide. What is the important parameter for the? What is the important thing for the MOS transistor? As we have seen, we have a substrate. We need to form gate oxide. Oxide is required, right? Oxide is required. On top of it, we have a polysilicon, and then we have to create a source and drain. This is what the process actually. So first I have done substrate, fine. Second one is I need to form gate oxide. But whatever the oxide that I have created, that's not a gate oxide. That is a field oxide. Okay. So what is the difference between the gate oxide and field oxide? Okay. One important point is thickness. So the thickness of the field oxide is larger than the gate oxide. Okay. As much thickness as low for the gate oxide, that much better performance can be observed for the mass transistor. Okay. So for a better MOSFET operation, gate oxide thickness must be very, very small. Very small thickness is required. Agreed? Okay. I think if you say that that is 100,000, few thousands of angstroms that we have taken, it is maybe 10 angstroms or 20 angstroms, something like that. That is the difference. You observe few thousands of angstroms to maybe 10,000, 10 angstroms or 20 angstroms that we have to consider. Okay, that is the difference. That is one difference. Thickness is one difference. The second one is that purity of the oxide is very, very important. The purity. That means what exactly meaning of insulator? Anyone from the class? What exactly meaning of insulator? Hmm? Yeah. So I can say that there is no free carriers in it, right? There should not be any kind of free carriers. If you say the conductor, n number of free carriers, so a lot of free carriers will be there, right? If you take up a semiconductor, also have got free carriers. In case of insulator, there should not be any kind of free carriers. Okay, but unfortunately, when you perform some kind of operations, maybe the process of forming the silicon dioxide, immobile charge carriers will be there in the silicon dioxide. Immobile charge carriers are there in that process. Okay, so that makes that can disturb the operation of the mass transistor. Okay, so the almost one important fact. So the theory of the MOSFET is well before the bipolar junction transistors. Okay, so the theory of the MOSFETs, but they were not able to realize the mass transistor for the first time. Why? Because they are not able to manage the gate oxide. So getting the 100% purity of the silicon dioxide is a very, very difficult task. That's the reason why they were not able to make the mass transistors well before the bipolar junction transistors. That's the reason why almost for a long years bipolar junction transistors are there in the IC technology. Later, advancement technologies are there, very controlled doping concentration they are maintaining. So therefore now they are able to realize the gate oxide perfectly. So now the MOSFETs almost the 40 to 45 years, there is no back of the mass transistors. They are in the leading in this IC technologies, right? So therefore that is the importance of this gate oxide. Okay, so therefore I should not use the field oxide as a gate purpose. Okay, therefore I have to remove some portions of the field oxide. I have to fill the gate oxide on that particular place. So for that one, I need to remove the selected portion of the field oxide, right? అంతే కదా, నాకు మిడిల్లో కావాలి, ఆ మిడిల్లో ఉన్న పార్ట్లో ఉన్న ఫీల్డ్ ఆక్సైడ్ తీసేయాలి నేను దాన్ని ఏమంటే మనం we can call it a selective removal of silicon dioxide. So if you want to do that one, we are going to use the technique called photolithography process. The selectively removal of silicon dioxide is called photolithography process, right? So with the help of this one, we can do. How can we do this one? It requires some kind of steps. Okay, we have to follow some kind of steps there on that one. What are those steps here? First, we have to form a photoresist material on top of the silicon dioxide. Generally, it is a polymers actually. We have to place a polymers on the field oxide on top of it. Okay, and then we have to define the mask here. And we have to define the mask here. That means at which place actually we want to remove the portion. Okay, so therefore this mask is very, very important. What exactly mask is all about? It's nothing but a glass plate. Okay, for example, this is an IC. For example, I'm going to use one glass plate here. Okay, so I can coat with a black color this glass plate. I can place it on top of the IC. Now I am going to allow the radiation on top of it. So this is what the radiation actually. So the UV radiation I'm going to have. So what will happen? So the light is exposing on on the mask or a glass plate. So some portion of the light is transparent on the photoresist material. Okay. Some light is not at all transparent or cannot pass through that obstacle. Okay. So what will happen here when the light is exposed to this photoresist material, the characteristics of the photoresist material will change. Okay, generally it is a hard material. Polymer is a very hard material. Photoresist material is very hard generally. As soon as the light is exposed to its characteristics will changes. That is becomes a soft one. It becomes a soft one. Okay, other materials are also there. Some polymers are initially very smooth one. When the light is exposed to, it becomes hard. That kind of photoresist materials are also there. Okay, but here in this process we are using the here we are using the initially the polymer, the photoresist material is a very hard material. When the light is exposed, it becomes very hard. Okay, I think it is not like that. Yeah. So this portion is actually initially it is a smooth one. So in this particular purpose, actually, I'm talking about. And when the light is exposed, this portion becomes very hard, and this becomes very hard. Okay, this portion becomes very hard. Okay, the middle part is very smooth. So if you are doing something like that, what will happen? This portion, the polysilicon, as you can see here, this portion of the polysilicon is very hard. We cannot remove. This portion of the polysilicon is very impossible to remove that part. Okay, but middle coating can easily get removed by etching process. By using the etching process, we can remove that one. Now, this particular portion is vacant now. So what I'm doing here, you can observe here, I have a field oxide. On top of it, what I'm doing, so this is the polysilicon I'm using here. So not polysilicon, photoresist material. And middle part I'm able to remove by using the etching process because very smooth one I'm able to remove that. Right. So this portion is there now. So this portion of the silicon dioxide I need to remove. Then it is not possible by using the etching process. It is by using the hydrofluoric acid solution. So that means we have to dip this material into the hydrofluoric solution. Automatically, this portion will get removed. Okay. But what about this? What about this silicon dioxide? Why it is not get removed? Because that is covered by photoresist material. The hydrofluoric solution cannot remove the photoresist material. Okay, so therefore, whatever the material under the photoresist material, that is not disturbed by the hydrofluoric solution. But middle part will be middle part can be removed very easily. So now the bare silicon is something like this. Okay, as you can see here, this is what. Oh, sorry. So this is what we can say that. What is the time? Yeah, we have time. This part is there. Now we can see the bare silicon at the middle. Can you see that one? Bare silicon at the middle. Okay. So therefore, later on, so our purpose is completed. So therefore, we should remove this portion, and we should remove this portion by using the etching process. Some kind of etching process are there. We can use that one. We can. Okay. Now this is what we can see. It's not possible that directly as per the textbooks they are giving that directly something like this, but it's not like that. It's not possible to do that. So some kind of curved nature will be there. Okay. So the steep kind of things cannot be possible to realize. Okay. So that's the reason why they have done something like that. Okay. ఇక్కడ వరకు అర్థమైందా అందరికి ఏం చేసాము how many steps that we have followed? The first one is field oxide. Second one, no, first one is field oxide. Crystal growth. Next one is field oxidation. Third one, photolithography process. What are the steps in photolithography process? Photoresist material, mask definition, UV radiation. Okay. So therefore, the final question is that, is it possible to remove the silicon dioxide directly? Is it possible to remove the silicon dioxide directly? So as I'm saying that, just put it in the hydrochloric solution. What will happen? All the silicon dioxide will get removed, right? That is not our purpose. Yes, we can remove the silicon dioxide completely, but not partially or selectively. If you want to have a selective removal, what we have to do? Definitely, we have to do the photolithography process. Agree? Now, this is the thing that we have to do. Now, let us quickly move on to the next one. The next one is gate oxidation. Next one is gate oxidation. So this is also called thin oxide. Field oxidation, what we can call as field oxidation? Thick oxide. This is called thin oxide, right? Very, very thickness is very small. Just we have, of course, the process is the same. The process, how to form the silicon dioxide is the same, but very controlled manner that we have to do it. Okay. Very controlled manner that we have to do it. Okay. Somehow we have realized the silicon dioxide on top of it. Okay. Here is the thick oxide. 1 micron thickness, for example, it is 0.1 microns. So very, very huge differences there. As you can see the diagram, 0.1 micron. Okay. So 1/10 of the field oxide will be considered as a the thickness of the oxide that we have considered, right? Okay. So therefore, as I mentioned, that the purity as well as thickness is the most important parameters for the gate oxide. Please remember this point. Okay. Now on the next step is gate realization. The next step is gate realization. So the gate realization is we are going to use polysilicon. Polysilicon. So how do we form a polysilicon? One question. So actually, it is a chemical vapor deposition technique that we have to use. What we have to use? Chemical vapor deposition technique. That is called CVD technique that we have to use. Yeah, I have written here. CVD technique. See, yeah. So if you want to do some kind of deposition on top of it, generally we use CVD technique, chemical vapor deposition. That means we have to put it in a gas chamber and allow the gas some what type of polysilicon atoms. Thus, we have to allow the polysilicon gas atoms on top of it. It can form polysilicon. Okay. So because of this polysilicon, we are calling as a polysilicon gate technology. Okay. Nowadays, from 65 nanometer technology onwards, people are using the metal gate technology again. They have come back to the metal gate. As what will happen, the sheet resistance offered by the polysilicon is very, very high as the technology is shrinking. Okay. So that's the reason why using the polysilicon is not suggested for the advanced technologies. Therefore, again, they have come back to the metal. So very, very interesting thing actually. They have again come back to the metal gates now. Okay, but it's okay. It's a different thing. Okay, now, now I'm going to remove the, I'm going to introduce the source and drain. I want to realize the source and drain, for example. Can anyone tell me what we have to do? So something like this I have. చూడండి ఇక్కడ నేను ఇప్పుడు ఏం చేశానంటే I have my oxide. On top of it, I have a field oxide. Okay, I have to take another color, for example. So this is the gate oxide. See, both are gate oxides only. Both are oxides only. Therefore, these portions are all these are the same. Okay, these portions all these are the same. But middle portion is very, very important for us. Okay. On top of it, what we are doing here? On top of it, we are going to provide a polysilicon. On top of it, we are providing the polysilicon, right? So the polysilicon and gate oxide, where it is exactly required? At middle portion only. Unwanted polysilicon we should remove. Okay. So therefore, for unwanted polysilicon, that means this is what unwanted polysilicon. This is also unwanted polysilicon. that can get removed by using the etching process again. Okay, etching process is used for two purposes. One is for photoresist material, for removal of the photoresist material. Second one is polysilicon. Okay, so therefore we can remove that portion. So once it is removed, something like this it is happening. I think it's better I have to have one slide here. I want to show that. Okay, see here. What is the time now? Another 4 minutes. Okay, we'll complete it 2 minutes within 2 minutes. Okay. So it is. This is all about, for example, the gate oxide. On top of it, we have a polysilicon, right? So polysilicon is available here, and other portions I have get removed. Other portions removed by using the etching process. This is what is happening actually. Now the question is that I want my source here. I want my drain here at this point. Of course, I don't want to go for along this one. Source and drain. Now, can anyone tell me what is the next step? I need to diffuse source material. I need to diffuse drain material. So oxide, polysilicon, we have N plus, we have N plus, right? MOSFET operation. Huh? Okay. So what will happen then? How do we diffuse this one? So okay. So that is the discussion for the next tomorrow's class. Okay. So it's the time is almost 5, sorry, 6. So it's not